Test on Friday, so we can clear things off for the March break. And we are almost at the end of the derivative and its applications. There will be one lesson that I'll just get you to complete on your own over the March break. Come the other side of the March break, we'll be all ready to start fresh. So, test on Friday tonight at 7:30. We're just going to do a class activity. It's called a game show. It will be a review for your test. If you can participate, that's great. That's one of those drop another test things if you participate enough. They're kind of fun, and I think they're pretty informative. It'll give you an idea what the questions might look like on your test. If you can't come, it's understandable. Here is your test and what you need to do. So you need to reproduce the product rule. So you have to use the limits and you have to use the properties of the limits to reproduce the property rule. It's kind of dumb in one way, but I think it's good in another, just for you to learn how those proofs work. So reproduce the product rule. You'll have to do one first principles derivative. And so that's where you use the function with limit as h goes to 0 of the difference quotient. You might have to do some sort of simple polynomial, x, well, definitely, let's just say it probably won't be x cubed because that's too much work for a test, but something with a polynomial or something with a radical or something with a reciprocal function. So you will need to manage the first principles derivative with the techniques we went over for either of those three approaches. Okay, you're going to need to find the tangent slope to some function at some point. In other words, you need to take the derivative. We have a power rule, we have product rule, we have chain rule. If you want, quotient rule, but you don't have to use the quotient rule. If you don't want to, you can turn it into a product rule. And so finding the tangent slope might be any of those. Find the equation of a tangent, and you should be spelling equation with a U, not like me. Once again, these are sort of the same game, okay? So any of the rules apply. And there will be a fancy question. All right, so fancy questions have variables, and then the information is given to you in sort of abstract forms. And so we've got f of x is equal to ax squared plus bx plus c. And we're given some information like the y-intercept is 5. The slope of the tangent when x is equal to 0 is 3. And the second derivative when f is equal to 1 is 2. And this is just a random integration that popped up. Okay, so something like that, there's actually enough information for you to basically figure out what A, B, and C are. So you can find out what C is. It says the y-intercept is 5. That means if you put a 0 in for x, you're going to be able to figure out what C is. The second derivative when x is 1 is equal to -2. If you take the second derivative of this and you just stay patient, you'll find out that it's 2 times a. And so that's going to tell you the value of a. And then the slope of the tangent, that's the first derivative. You can substitute your a value in and you will get the value for b. So that's an example of a fancy question that might be on your test. Okay. So once again, game show tonight. Come in if you can. You're just participating. It's not a video conference. You're just basically playing a review game online with your classmates. And so we've looked at sketching the first and second derivative. And this is sort of a broad strokes lesson. And so we actually do this a little bit more in depth. This just introduces some concepts that, that it's sort of important to be familiar with when we get in a little bit later into the course. And so here's my function. I'm just going to label it f at x. But of course, you guys have all taken advanced functions, and so you probably recognize this is a cubic function, most likely. Not all of them will be cubic later on in the course, but it's a cubic function. And so first thing we're going to do is we're going to sketch f primed at x, or sketch y equals, and I suppose I should say y equals f primed at x. And so when we sketch what f primed at x, basically what we're doing is we're looking at the first derivative, which means we're looking at the values of the slopes. So my first thing that I'm going to do is identify these locations that are known as turning points, or local maximums or minimums. Notice this is a local minimum because if I examine the function on either side, I can see that this point right here is the smallest value of the function locally. And this is a local maximum because it's the smallest value locally. But really, the minimum of the function is negative infinity, and the maximum is positive infinity. So that's why we distinguish local. Right here and here, we'll call this A, and at B, the slope is 0. And so if the slope is 0, that tells me that my derivative is 0. Okay, so at A and B, my slope is 0. So if I'm going for the derivative, that's where it's going to intersect the x-axis. So there we go. Let's call this C and D for the sake of argument. All right. Now we need to figure out, is the derivative below or above the x-axis? So all we really need to do is look at the slope of the tangent to this point of A. And as we approach A, that slope is always negative. And so this is going to be below the x-axis until we get to C. And right here at B, I can see that the slope goes negative again. And so it's going to be below the x-axis in here. Between A and B, I can see that actually my slope is always positive. And so it's going to be above the x-axis in this area. Now you can probably see this is a parabola. You might be able to see that this changes from what's known as a concave up curve to a concave down curve. And this is actually a point of inflection. But somewhere in here, we actually have the maximum of the derivative. So here comes my derivative. Okay, slopes are positive between C and D. There we go. There's my derivative. And it's a thing of beauty. I will accept no criticism on my derivative. So let's look at the second derivative. So let's sketch y equals the second derivative of x. And so the second derivative is the derivative of the derivative. So I can sketch my second derivative by looking at my derivative. And we'll try and relate it back to the original function. Okay, if I were looking here, I can see that the slope to my derivative function is 0 right here. And so my second derivative is going to intersect the x-axis down here. Okay, so slope of the first derivative is 0 there. My second derivative is going to have a value of 0 right here. And if I look at the slope of the derivative, I can actually see the slope is positive until I get to point E, and then after that, the slope is negative. Okay, so there goes f double primed at x. Okay, so positive in this region, and so the second derivative is above the x-axis. Negative in this region, second derivative is below the x-axis. If I go back to my original function, I can see that as we approach this minimum, the slope is increasing all the way until I get to E, and then the slope is decreasing beyond that. And so beyond E, the second derivative is going to be below the x-axis or negative, and before that, the second derivative is going to be positive. Okay, so that is sketching the first and second derivative from the original function. So it's just broad strokes. There's nothing terribly algebraic about it. But it just gets our minds on that whole idea of slope and the rate of change of the slope. Any questions?